So in part one, we've started by looking at the primary and secondary. Now, in part two, we are only concentrating in the primary refrigerants. So we can call, perhaps maybe I can call, instead of only refrigerants, I can call it primary refrigerants. So the primary refrigerants can be divided into or classified into pure fluids. So those are pure substance, one type of substance or chemical. Or they can also be mixtures where we mix two or more refrigerants to make another type of refrigerant. Okay, so we can divide them or classify them based on whether the refrigerants are pure fluids or whether the refrigerants are mixtures. So in terms of the mixture type of refrigerants, we will dive into them later, but we can divide them into azeotropic and zeotropic. And by the end, you should understand what azeotropic and azeotropic means, what we're referring by, if you hear the term that people use in azeotropic, but in general, all the mixture refrigerants, they are referred by blends. So if you hear the word blend with on a sentence of refrigerants, they are actually referring that that refrigerant is a mixture or a mixture refrigerant. So they're called blends. So that's one classification of refrigerants. We will dive in when we look at them. And the other are the pure fluids. And the pure fluids, we can divide them into synthetic or natural type of refrigerants. Of course, what I wanted to highlight here is the world of refrigerants is growing every day. A new type of refrigerant is being added every day. A new classification of refrigerants is being developed as we go along, because we are in the transition period. We will look at the historical transition period later. The synthetic, we've got the CFCs. So a CFC, it means chlorofluorocarbon. It means it contains chlorine, it contains fluorine, and it contains carbon. So those refrigerants, and those are a few of the examples of CFCs. HCFCs, so hydrochlorofluorocarbons. So it means it has hydrogen, carbon, fluorine, and chlorine. So again, every time I mention chlorine and fluorine, I want you to relate it to the index we've used, which is ODP. So you would know that refrigerant is not a zero ODP. It contains chlorine and it also contains fluorine. And you can then easily relate it to how what that impact then will be to our environment. And then continuing from there, we've got HFCs. So HFCs contains hydrogen, fluorine, and chlorine. Okay, and these are a few examples. And as we can see, R134A, which we were using as one of the experiment, is one type of HFCs. We've also got the HFOs, but indirectly, actually, the HFOs are HFCs, which I haven't added here. And if you look at the natural type of refrigerants, we can call them organic and inorganic. The organic are the hydrocarbons that we're referring to. Again, we'll look at the benefits, the pros and cons of using hydrocarbons, pros and cons of using the inorganic or the natural refrigerants in general. Because the way forward at the moment, people are talking about, low GWP refrigerants, or the way forward are the natural refrigerants. Hydrocarbons, whether they're organic or inorganic type of refrigerants. So that's the overall classification method. So purely based on whether the substance is a pure fluid or whether the substance is mixture to make another refrigerant. And in a minute, we will look at, so we've got the two types of mixtures where, we have other examples that we use in R500 to R407. And you will be able to tell me by the end, if I give you a refrigerant, you can easily tell me what family it belongs to, whether it's blend, whether it's zeotropic, whether it's azeotropic, or whether it contains, fluorine or chlorine. So that's the overall classification method. So far, as I said earlier, the world of refrigerant is growing and growing. And, every day we're developing a new type of refrigerants. And of course, over the years, a wide range of refrigerants have been developed. What we will look at in the next few slides is how the designation of each refrigerant can actually tell you quite a lot of information. Okay, so far, the only refrigerant that we've used as an example in the lab is R134A, the designation, what it means by R134A. But now it's time that actually it can tell you the chemical composition of the refrigerant by just looking at the value R134A. It can tell you the molecular weight. One can get quite a lot of information by just only looking at the designated refrigerant number. So all refrigerants, they all start with they're designated by R. Okay, so to show it's a refrigerant, we start by R, and then followed by a unique number. Okay, so R134A, R11, R22, R, etc., etc. Okay, so we all start with the value designated letter R, and followed by a unique number. And let's look at what an Azure standard. So going back again to Azure standard 34, some refrigerants, for instance, may start with values between 0 to 100. So R11, R22, R12. Okay, any number between 0 to 100. And if you've seen refrigerant, for instance, R11, R22, etc., etc., you would know those refrigerants are methane-based refrigerants by just only looking at the designated numbers. And if refrigerant starts with 100 series, it might be the first refrigerant that we've looked at, R134A. You know R134A is an ethane-based refrigerant. If the refrigerant starts with R200 something, then we know it's a propane-based. R300 the same, a propane-based. R400, we know, in a minute we'll dive into it, but we know if a refrigerant starts with R400, we know it's a zeotrops. We will define what a zeotrop and azeotrops means. So by just only looking at the refrigerant and the number, you can tell me actually what family belongs or what it contains in there. And the same with R600, that if you look at the series number, you can actually tell me what that refrigerant contains. Okay, so we'll dive into some of them, and you should be able to easily derive the chemical formula or chemical compound of each of the refrigerants. Okay, so in the next slide, let's start to learn how to read the designation values of the different types of refrigerants. We will start by looking at the fully saturated or halogenated compounds, and these halogenated compounds, they are derivatives of the alkanes. So don't worry about the chemical formulas that you have here, but a good example of this is the methane, and we will use methane as an example, or ethane, CH4 or C2H6, and we will actually look at in a minute how to derive the chemical composition for a halogenated type of compounds. So we will learn how to read the designated values for halogenated type of refrigerants. So the rule is, as we said, every refrigerant starts with the letter R. Okay, and then followed by a unique value. We will call those unique value X, Y, and Z. At this point, of course, we don't know any of them, but the important one is they all start with R and followed by a unique value. And those unique value are X, Y, Z, and we will know actually what those unique value tell you. Okay, what the value of X tell you, what the value of Y tell you, and what the value of Z tell you. Indirectly, they all tell you. X tells you the number of carbon, how many number of carbons there are in that refrigerant, carbon molecules. Y tells you the number of hydrogen, and then Z tells you the number of fluorine in that refrigerant or in that substance. Okay, we will use, so X plus 1 would tell you the number of carbon, Y minus 1 would give you the number of hydrogen, and the value of Z will give you the number of fluorine. We can also use, so now we know the carbon, we know hydrogen, we know fluorine. There's one thing that we don't know at this point, and we have to use the balanced equation to find the chlorine, number of chlorine. And to find the number of chlorine, it is the hydrogen plus fluorine plus chlorine should give you 2 times number of carbon plus 2. Okay, so from here we are able to know the number of carbon, number of hydrogen, number of fluorine, and using the balance equation we can find the number of chlorine easily. Okay, we'll use as an example so you understand what we're referring. So that's what we're referring by Rxyz, and how x plus 1 gives you the number of carbon, y minus 1 gives you the number of hydrogen atoms, z gives you the number of fluorine, and the balance, of course, to find the chlorine is hydrogen, fluorine plus chlorine. It should be equal to the number of 2 times carbon plus 2. Often, although we're saying that Rxyz, there are 3 numbers here. Often you may come across refrigerants with only 2 values. For instance, R12, R11, R22. So what that means is that the number of X is 0. Okay, so in a minute let's look at which example that we've used here. We will calculate the chemical formula of R22 as an example. Okay, and to do that, let's start from here. So the first equation that we need to write is R, X, Y, Z. And we want to know R22. So R, remember, if there are 2 values, the number of X is 0. So it means R022. Okay, so using this arrangement, let's find the number of carbon, the number of hydrogen, and the number of fluorine. So we said X plus 1 gives us the number of carbon. Yes. So 0 plus 1 should give us the number of carbon. So 2 minus 1 should give us the number of hydrogen. And finally, 2 will give us the number of fluorine. We know the number of carbon, we know the number of hydrogen, and we also know the number of fluorine in that substance. So let's work out the number of chlorine using the balance equation. Okay, so here, hydrogen plus fluorine plus chlorine should be equal to 2 times carbon plus 2. 1 plus number of fluorine, 2 plus chlorine should be equal to 2 times 1 plus 2. So we can easily work out our chlorine. So 1 plus 2 is 3 plus chlorine equals to 2 times 1 is 2 plus 2 is 4. So number of chlorine equals to 4 minus 3, which is 1. So now we know every atom in the substance. We know the number of carbon, we know the number of hydrogen, we know the number of fluorine, and we also know now the number of chlorine. So carbon, hydrogen, chlorine, and carbon, then hydrogen, then chlorine, then fluorine. All right, so let's put that together in here. So we know how many carbon did we have? From here, we only had 1 carbon, right? So it's C. Number of hydrogen, 1. And number of chlorine is 1. And number of fluorine is 2. So F2. So that is the chemical formula for R22. So number of carbon, number of hydrogen, number of chlorine, and number of fluorine. By looking at this chemical formula, you should be able to tell me actually the substance contains carbon, contains hydrogen, it also contains chlorine and fluorine. Therefore, you know it's not a 0 ODP refrigerant. So we need to do R12 and R134A. So we don't consider the letter at the end when we calculate or when we estimate the chemical formula. Let's start with R12 and we'll do the same exercise. So I'll transfer R12 into Rxyz. So we know R12 could be written as R012. So that means R012. And then we can find our number of carbon, hydrogen, and fluorine. Now we know the value of X, value of Y, and the value of Z. And just to remind you, X plus 1 gives you the number of carbon, Y minus 1 gives you the number of hydrogen, and the number of Z gives you the number of fluorine. So let's do that here. Number of X is 0 here. 0 plus 1 would give you the number of carbon, Number of Y is 1. 1 minus 1 would give you the number of hydrogen, and 2 would give you the number of fluorine, or the number of value of Z would give you the number of fluorine. Okay, so now we know the number of carbon atoms, hydrogen atoms, and fluorine atoms in that refrigerant. And let's do the balance equation. Hydrogen plus fluorine plus chlorine should be equal to 2 times carbon plus 2. So we know the number of hydrogen, 1 minus 1, which is 0. Number of fluorine, it's 2. So that's 0 plus 2 plus chlorine equals to 2 times number of carbon is 1 plus 2. So we can easily find number of chlorine is equals to 4 minus 2, which is 2. So let's put the formula together. So what's the number of carbon? 1. So it's C. What is the number of hydrogen? We know the number of hydrogen is 0, so we don't have any hydrogen in it. And the number of chlorine we've just calculated, which is 2, so 2 chlorines. And the number of fluorine we've calculated here, which is 2, F2. So the chemical formula for R12 is CCl2F2. So one number of carbon atom, 2 chlorines and 2 fluorines. So indirectly, if someone was to ask you, so what type of refrigerant is this? So that is CFC, right? CFC. So you can easily tell R12 belongs to CFC types of refrigerant. It contains carbon, fluorine, and chlorine. So let's do R134A. So the same R, X, Y, Z, and let's put R134A. We don't use the letter A. So we know the number of X, we know the value of Y, and we know the value of Z. So X plus 1, so that is X plus 1 will give you carbon, Y minus 1 will give you hydrogen, value of Z would give you the number of fluorine. So X is 1, so 1 plus 1 equals to carbon. Number of Y is 3, 3 minus 1 will give you the number of hydrogen, and the number of Z is the fluorine, which is 4 equals to number of fluorine. So now that we know carbon, hydrogen, fluorine, we can perform the balance to calculate the number of chlorine. So hydrogen plus fluorine plus chlorine equals to 2 times carbon plus 2. Number of hydrogen plus number of fluorine is 4 plus chlorine equals to 2 times number of carbon is 2 plus 2. So 6 plus chlorine equals to 2 times 2 is 4, 4 plus 2 is 6. So therefore, number of chlorine equals to 6 minus 6, which is 0. So we don't have any chlorine. So let's put the formula together by looking at the carbon, hydrogen, chlorine, and fluorine. So how many number of carbon do we have? 2. Number of hydrogen. Okay, so the number of chlorine, the number of carbon we've said from here. So number of carbon were 2. Number of hydrogen were 2. 3 minus 1 again here. So 2 hydrogen. Number of chlorine, we've just worked out there's nothing, we don't have any chlorine in the refrigerant. And number of fluorine, we have 4. So we know the chemical formula for R134A is C2H2F4. And if one asks you which family does R134A belongs, you know it is HFC. It contains hydrogen, fluorine, and chlorine. And as you can see from here, hydrogen, fluorine, and chlorine. And the second designation method, and how you can easily read, is the inorganic refrigerants. Okay, and the way you would know whether any refrigerant belongs to the inorganic refrigerant is it starts with the number 7. So it starts with R, then followed by number 7. So if you've seen any refrigerant which starts with the value R and then number 7, you would automatically know it is inorganic refrigerant. Okay, and the following number after 7 is actually the molecular weight of that specific element or molecule. Okay, so we'll look at it as an example. For instance, we'll look at ammonia, carbon dioxide, and water. So we were looking at the inorganic refrigerants and how every inorganic refrigerant starts with the value R and then followed by 7. And the remaining values are actually the molecular weight of that substance. Okay, so let's look at ammonia as an example and how you can easily read the chemical formula for ammonia or the designation. So those type of refrigerants are the inorganic or natural refrigerants. And we will learn now how to actually read the designation for each of the refrigerant. Okay, so we said each inorganic refrigerant starts with the value R followed by 7 and followed by the molecular weight of ammonia. So molecular weight of, we have 1 molecule, and nitrogen 14. Okay, so if you add the total number of atoms in the nitrogen and hydrogen, so we've got 14 nitrogen. Hydrogen, we said 1 times 3, it's 3 plus 14, so we've got 17. So the molecular weight of ammonia is 17. So the designation for the ammonia as a refrigerant is R7 and then followed by the molecular weight R717. So if you've seen a refrigerant with R717, you would automatically know it's refrigerant, it's ammonia. Okay, let's do the same for water. As we said, we start with the value of R7. So we know hydrogen is 1, 16, thank you. So 16 oxygens and hydrogen is 1 times 2, 2 plus 16, 18, right? So the way you would write water as a refrigerant is R718. So if you've seen in any label it says R718, you will automatically know it's inorganic, but you also know by the molecular weight it is water. By the molecular weight, you know it's ammonia. And let's do finally carbon dioxide. R7, 12, and oxygen 16, right? So 16 times 2 is 32 plus 12, it's 44. So R744, if you've seen before, it's actually CO2 as a refrigerant. All right, so the telltale signs are, if it starts with 7, R7, you know it's an organic or natural refrigerant, and followed by the molecular weight. So at the beginning, when we've looked at the classification method, we've also looked at some of the refrigerants are mixtures and sometimes termed as blends. Okay, so if you hear the term blends, they're referring to the mixture types of refrigerants. And the reason why we mixed 2 or more refrigerants is, of course, in order to deliver the best properties, the best thermodynamic efficiency of the system. It might be an improvement, there might be an improvement in the safety, there might be improvement in terms of the cost if you mixed 2 or more refrigerants to make a new refrigerant. So in the picture you can see R404A, I think one of the refrigerants we've talked about earlier. So indirectly, of course, in the picture I'm telling you it's a mixture type of refrigerant. So by blend, whenever you hear blend, we're referring to the type of mixed refrigerants. So they are mixed type of refrigerants. Or what do you think may arise by mixing 2 or more different refrigerants to make one refrigerant? What may arise if you mix 2 or more different refrigerants? Okay, so not all blends behave this way, but certain blends or certain mixtures, if you mix refrigerants, 2 or more refrigerants together, they start to behave differently. So they start to behave differently. Instead of behaving in terms of the boiling point or the freezing point of the new refrigerant, instead of behaving one, they start to behave differently because they are 2 or more different refrigerants. So they start to exhibit what we call temperature glide. And that's the word that everyone uses in discussions when they talk about blends. there's a temperature glide. What a temperature glide means is, if you look at the graph here, ultimately a pure refrigerant have a constant saturation temperature, or a constant saturation pressure. So in a pure refrigerant boils and freezes at a constant pressure. So in the evaporator, it boils at a constant temperature, constant pressure, and in the condenser, it condenses at a constant temperature and pressure. So when we looked at the vapor compression cycle in the past, we knew the black part, or that line, or your condensing pressure and your evaporating pressure are constant, because we know pure fluid only behaves one way. It freezes and it boils at a constant temperature or constant pressure. That's the advantage. But once you start mixing two or more refrigerants, they start to behave differently. Instead of having a constant or one behavior, they start to give you a temperature glide, where instead of boiling or freezing at a constant temperature, they start to give you a range of temperatures where before they boil or before they condense. Okay, and that is of course a problem. Instead of having a constant saturation temperature or constant saturation pressure, you will end up having a range. So if you look at the one highlighted in blue, that is the range of your condensing pressure. So instead of having a constant condensing pressure, you will end up having that range of condensing pressure, and the same with the evaporating pressure. So you have that range. So they start to exhibit different behavior for the different types of refrigerants that you're mixing. And that's what they call temperature glide. That's what we're referring by temperature glide. And as I said, in most of the discussions, and when it comes to blends, the first thing that people would say is, but blends, they exhibit temperature glide, and they're all it means is that because we're mixing two or more refrigerants, some of the mixture, I'm not saying all of them, but some of them starts to behave differently, starts to the saturation temperature and saturation pressure, they give you a range. Okay, so that's what we mean by temperature glide, and that's what we refer by some of the weakness of the blends. We will look at in a minute. Not all of them exhibits the temperature glide, not all mixtures or not all blends. The refrigerants or refrigerant blends that do not exhibit the temperature glide, they're called Azure Tropic blends. Remember at the beginning when we had the classification, we were talking about zeotropes and azeotropes. So the term Azure Tropic, we are referring to the mixture of refrigerants, but they do not exhibit the temperature glide. So they don't have the temperature glide problem. So those mixture of refrigerants, they still behave as similar to the pure refrigerants. They do not have that exhibit. So they have a constant saturation, condensing and evaporating pressures. And they are called azeotropic. So as you can see, R tells you that they don't have that problem. Okay, azeotropic blends. And those refrigerants, they all start with R500. Okay, they are 500 series. Few examples of the azeotropic. As you can see, we've got a refrigerant called R500. And that R500 is actually a mixture of R12, 73.8%, and R152A, which is 26.2, to make that new refrigerant R500. And the same with R503, R507A. So you'd know actually by only just having the number R500, you know it's blend, you know it's a mixture, but you also know that it does not have the temperature glide problem. You know it's azeotropic blend or azeotropic type of refrigerant. Okay, and of course the other side are called the zeotropic refrigerant blends, and that tells you actually those family or those type of refrigerants, they have the temperature glide. Once you start to mix those refrigerants, they would have different saturation temperatures and saturation pressures. Okay, so therefore they have that temperature glide, and they're called zeotropic. So by now, you know what azeotropic and zeotropic blends are. Okay, and those refrigerants, they start with the series 400. So if you've seen a refrigerant, for example, R404A, we know it is a blend. We also know, because it's a series 400, we also know that actually it also exhibits the temperature glide. It has its weakness is that it does not have a constant saturation temperature and saturation pressure. Okay, so that's what we're referring by mixtures, by blends, and how certain type of blends exhibit temperature glide, but other type of mixture refrigerants do not exhibit the temperature glides. Okay, and also we've looked at the hydrocarbons, and this is some of the few examples. And of course, we've been using the hydrocarbons successfully in industrial, commercial, domestic applications. These are a few examples that you can look at: the propane, N-butane, isobutane, etc., etc. So those are the hydrocarbon type of refrigerants. And this table should summarize, will give you the different types of refrigerants and the applications used for each refrigerant, and the potential substitutes or suggested substitutes for the given refrigerants. Some of them may have been already phased out, or some of them may be or will be phased out shortly. So you can see it gives you just a summary of the different few of the refrigerants, their thermophysical behavior or property of the refrigerant, where it's used in terms of the application, and of course the potential replacement of each of the refrigerants. So there's more here, which applications, or potentially what can we replace it with. So I want to show you this slide. So to give a context, this diagram, it gives you an overall feel of the development and transition of refrigerants. The transition of refrigerants starting from early 1800s, 1834, okay? And then, the types of systems they were using, or the cooling aspect they were dealing with, the refrigerant that they were using were mostly natural refrigerants. We're talking about early 1800s, okay? But of course, with time, we started to transit, and then we started to introduce some chemicals, of course, to try and make it better in a range of thermophysical aspects. So by 1930s, we've started using R12, R502, and then we went all the way to 1980s. In the 1980s, some examples are the R22, and then we've looked at the 1987 earlier in the slide, and how people started to do research and started to find out actually CFCs, are impacting our environment, especially our ozone layer, and that's where the Montreal Protocol was trying to address the impact of refrigerants with CFCs specifically. Okay, and then going forward in the 1990s, we started using R134A, R404A. So now, when I speak about these refrigerants, you should be able to automatically tell me, okay, yeah, R404A, he's talking about blends. He's talking about these R404 have temperature glide. So you should automatically be able to tell me as I go along, as I mentioned some refrigerants. So, and then, of course, by around 1997, we had the Kyoto Protocol, again, to see if we can phase some of the refrigerants or develop and look some alternative refrigerants, okay? And all the way from 1997 to 2010, all the way to 2014. And 2014, we had a revision of the F-gas regulation, where it deals with the refrigerants which use fluorinated or contains fluorine in them in 2014. And of course, that regulation is a widely used regulation, a European regulation that we follow when it comes to using refrigerants. And from 2014 up to here and looking forward, the projection is that actually, we're phasing out as we go along. So a range of different types of or families of refrigerants have been phased out, and some of them are in the process of phasing down. And the alternative that the industry and a range of research is indicating is actually the best alternative refrigerants to go or to use is the natural refrigerants. And as you can see how history is repeating itself. Although we've started using the natural refrigerants in the early 1800s, we went through this cycle, introducing chemicals. We transitioned and developed a wide range of refrigerants, but actually we're going back to the original refrigerants, and we're saying the alternative refrigerants now. If you look at, the alternative refrigerants that they're suggesting, is the best choice from an environmental point of view are the natural refrigerants, because as we can clearly see, they do not contain chlorine, fluorine, or bromine. So therefore, they are zero ODP or substances. Okay, so that would give you a context through the development and transition of refrigerants from early 1800s all the way to now and looking forward. Now let's quickly have a look at some of the pros and cons of, because we're saying that the way forward is natural refrigerants, and let's quickly have a look at the pros and cons of using some of the refrigerants, ammonia, hydrocarbons, and carbon dioxide. Okay, what's the advantage of using carbon dioxide as a refrigerant, or what do you think is the drawback? Non-flammable. CO2 or carbon dioxide is non-flammable.
Do you need to use quite high pressure to get it to change state?
Yes, that's another drawback or the weakness of or disadvantage of using carbon dioxide, that it operates at a very, very high pressure. Therefore, all the materials that you require that we normally use for our normal systems are often difficult to accommodate when you're using carbon dioxide. And the fact that if you're operating at a very, very high pressure, again, going back to your vapor compression lecture that we did, what happens if you increase your condensing pressure? What happens to your compressor? And what happens to the efficiency of the system? Okay, so if you're using CO2, yes, we tend to have a very low efficiency due to the fact that we are operating at a very, very high pressure. So looking at some of the advantages and disadvantages of carbon dioxide, as you guys said, it's non-flammable, it's non-toxic, and it's relatively inexpensive compared to other type of refrigerants. And if you look at the drawbacks, the primary drawbacks that everyone talks is the fact that we operate at a transcritical process where the pressure is extremely high. And of course, the effect and impact of having a very high pressure is a system struggles. So you would have a low efficiency. Okay, so that's one, looking at the pros and cons or advantages and drawbacks of using carbon dioxide. So if you look at the hydrocarbons, we have been using them, again, 1800s. They have zero ODP and a very negligible GWP or small GWP. So at this stage, of course, you should be able to know the difference between what ODP means, what a GWP means. And of course, going forward, they are a good substitute for the CFCs, HCFCs, and HFCs. They are compatible with copper, and they tend, if you look at the thermodynamic efficiency or energy savings, they tend to have up to 20% due to the lower molecular mass of the refrigerants that we have. But one of the drawbacks of using hydrocarbons is they are flammable. Okay, so that's again one of the pros and cons of hydrocarbons. Let's go back to ammonia now. So if you look at ammonia, of course, it's a naturally occurring substance, and it has actually zero ODP. It means it doesn't contain chlorine, fluorine, or bromine, and it also have a zero GWP. So ideally, when we talk about environmentally friendly, ammonia is way at the top in terms of ODPs and GWPs, and it also have an excellent thermodynamic characteristics. Again, similar to the hydrocarbons due to the small molecular mass. Okay. Now we can look at the smell through two dimensions. We can use the smell, the fact it gives us a platform or an opportunity to be detected early, because a very small concentration of ammonia, you can smell it from far. So That we can take it as a positive in a way that we can easily detect it if you're able to smell it from far. But of course, the disadvantage, and it's relatively low cost compared to the other refrigerants. But of course, the drawback is toxic, flammable at a concentration or between 16 to 28%. It tends to be it's not compatible with copper, and I think I've mentioned about this at the beginning. And of course, temperature on the discharge side of the compressor is also higher compared to other refrigerants. Okay, so although it has an excellent thermodynamic aspect, it's a very environmentally friendly, but the fact is very toxic, could be flammable at certain concentration. And of course, there are regulations and legislations that deals with the amount of refrigerant that you should use in a given areas. So that is a quick visit on using the natural refrigerants, because we said alternatives going forward. It's about the natural refrigerants: ammonia, carbon dioxide, hydrocarbons, and we've also looked at the pros and cons, advantages and drawbacks of the refrigerants. And at the end, we're looking at ammonia and how a very small concentration could be toxic. And that's where we come back to some of the legislations that